All right, welcome everybody to week 15, day 1 of Computer Science 41. And today we're going to be talking about how to make your programs go fast. And there's a lot of answers on how to make your code go fast. The one that you might have learned on the ELO assignment was turning on the optimizer. So if you tried running your code without -03, none of your timings mean anything, because if you run your code, if you compile your code without the optimizer on, then it does not generate code that is supposed to be fast. It generates, in fact, terrible assembly. If you look at the assembly code that comes out of the compiler with the optimizer off, it is garbage. It loads a variable from RAM and then stores it back in RAM, and loads it out of RAM and stores it in RAM. It is really slow. And if you -O fast is actually an option too. I know you're joking, but that's actually an option. If you do -O fast, then it can break correctness on floating point numbers to get extra speed. So like when I first did the ELO assignment, a student was like really struggling to like make his code go faster, and he'd done things like use a hash table. Or, in general, pick the right data structure for the job. Like that makes a huge difference. If you go from order n squared to order n, like that is a fast speed up, right? Like that's monumental. You have a million things. Instead of doing a million things, you do a million things. So it's a million times faster. Like the optimizer isn't going to give you a million times speed up usually. Usually the optimizer is going to give you, I don't know. It really depends on the application, but it might run twice as fast or 3 times as fast or 10% faster. It just kind of depends on your application. But if you're doing any of this stuff, trying to make your code go faster and you don't have the optimizer on, you're doing it wrong. Like the first time I ran it, like I had the student, he's sitting there like messing with the data structures, he's doing all this stuff. And I'm like, have you turned the optimizer on? He's like, what's that? I'm like, okay. So you need to go into your makefile and add -03 to, you type G++ -03. And that turns on the optimizer at full power. There's 01, 02, 03. There's other options. There's millions of options for optimizers. But 03 is, generally speaking, the fastest one that shouldn't break correctness at all. And what that does is it makes the assembly that comes out of the compiler like good. And like you can see pretty substantial gains in performance. And so some students were asking like why C++ 17 was way slower than C++ 25 for the same code. And the answer is it shouldn't be. Like there's nothing really like that significant that changed between 17 and 20. I mean, they have more header file options and things like that, but in general, like there shouldn't be a massive speed difference like my students were saying. But at the same time, they were not turning the optimizer on. And so like none of the timing you get means anything when the optimizer's off, because it just generates bad assembly. Like it just generates like really, really slow assembly. And so if you're comparing running times of things with the optimizer off, it's nonsensical. Like don't do it. Like the only time you should ever be comparing running times is with the optimizer on. And if you turn the optimizer on, I don't think they saw any difference between 17 and 20 in the G++ mode. Also, you should know that on the server, C++ 25, 2A. If you become Aaron, if you look at the alias we have set up for G++, like some students are just compiling it by hand. We have 3 different safety measures turned on. We have this, which turns on the safe standard library. So if you have a vector and you use square brackets with it, it will do bounds checking, even though it's not supposed to. It's pretty nice. If you try popping off an empty stack, it'll throw an exception. Normally, the standard library doesn't. Normally, the standard library will segfault if you pop off an empty stack. But if you have the safe standard library on, then it will give you a nice error message. We have the undefined behavior sanitizer turned on, which looks for different kinds of undefined behavior when the program's running. And we have, of course, address sanitizer. Address sanitizer is life, especially whenever you're working with pointers or news and deletes and things like that. You want to have address sanitizer on. When you don't want it on, when you do not want it on, is when you're trying to benchmark your code. And you're trying to get your code to come in under the 3-second limit. Address sanitizer slows your code down a lot. So what you typically do when you are coding is you will have debug and you will have release. And so you'll see people type make debug like this, and you'll see people type make release like this. And there are two different options. Like when you type make debug, it'll compile all of your code with address sanitizer turned on and the safe standard library, all that kind of stuff. And then when you're ready for it to be fast, then they will make clean and make release and compile it with the optimizer turned all the way up and all the safety features turned off. This is standard practice. If you fire up Visual Studio will have these two options on. Like if you just make a blank project, it creates a debug and a release version for you. This is extremely common in the real world when you're working for a company, because when you're developing, you want it to catch all of your mistakes. Like if you dereference a null pointer, you want it to be like, boop, line 40, you dereference a null pointer. Don't do that. You want it to catch that. But in release mode, hopefully you've caught all of your bugs or all the important ones. And so in release mode, you want it to be fast and not do all those checks, because hopefully all those checks have checked out and you're not making dumb mistakes anymore, and your code will run fast. So what is a .sh file? A .sh file is a shell script file. So if you cd into elo and you look at the timing thing here, make time it. So it is going to give you the running time of the program. So a .sh file, this one right here, is a shell script. So it's a series of commands you can save into a text file. In this case, it is just running your a.out. Time is going to give you the running time of it. It's going to feed in input file 19, which is the big one, and it's going to redirect the output into dev null. So this is going to tell you how long your test 19 is taking, so you can know if you're coming in under that magic 3-second limit. So under his makefile here, Aaron does not have -03 turned on. So let's do that for him. Turn off debugging. Let's see. I'll make a macro for this. So what do we want to do? QQ to start recording macro Q. Visual mode, I'm going to select all of this. Substitute -03. Any other things I want turned on? I guess that's fine. Go down a couple lines, go left here, and hit Q to stop recording. Now if I hit @Q, it does it again. If I hit @, it does it again. So I don't have to repeat myself. So macros are life, and so now I'm going to make clean and make, and it is going to rebuild now in release mode. And so now if I run time it, we'll see if it runs faster. In fact, it went from, what was it, 1.7 seconds to 1.3 seconds. So his code just got 30% faster as a result of the optimizer being turned on. Probably should turn on C++20 mode also, because some students were reporting a difference for that. So we'll go -std equals C++2a. Come down to here, hit dot for an instant macro, and hit dot for an instant macro. It repeats the last key that you did. Make clean, make, and then we will run time it again. And it doesn't seem to make that big a difference. So these are the kinds of topics that give you imposter syndrome about Seaside. You're not expected to know it. I'm teaching you right now. This is actually the time when you learn all this kind of stuff. In fact, the shell scripting you're going to learn in the next homework assignment. So you're not expected to know it now. These are all good questions. Yeah. So you didn't turn the optimizer on. You're passing the test. All right, cool. Good for you. You don't need to. Like Aaron passed it without having the optimizer on, but you can see the optimizer made the code 30% faster, so 25% faster. And so there's learning all the different like -03 and -G and -S and all these kinds of compiler flags are things you just kind of pick up over time. And when you need them, I explain them to you. -03 is the optimizer. Like I said, the first time I did this, I had a student who was struggling, and I finally told him about it. And he's like, "I'm going to get a tattoo on my shoulder that says -03." So I never forget that again. Some hidden learning point. Yes, the optimizer was a hidden learning point for this assignment. Or a lot of students, they were not passing until they turned the optimizer on. If you pass without it, more power to you. It's hard to make a test case that won't fail students. That Okay. Right. So we're talking about dynamic programming today. And so coming back to our list of optimization things, the right data structure for the job, the optimizer, these are all really important. The right algorithm for the job. For example, let's say that you were going to sort something. What is the running time of sort for your generic best, optimal generic sorting algorithm? Order n log n is correct. That is the fastest sort algorithm you can have unless you know something about the data. If you know that the data is mostly sorted, you can use bubble sort. Bubble sort is terrible. Bubble sort, if you use bubble sort because you just didn't know any better, bubble sort is order n squared. So if you had 1,000,000 elements, you'd be doing 1,000,000,000 operations instead of 20 million for regular sort. So you're 50,000 times slower because you picked the wrong algorithm for the job. But bubble sort, also known as BS, is order n if only one item is not sorted. So if you have a sorted vector and you push back a new entry and you want to sort it, you know that all of the vector is sorted except for the last one. And so you can actually use bubble sort on it, and it will sort it in order in time. It'll actually be faster to sort your vector than if you just called the standard library sort. And this is one of the reasons why taking data structures and algorithms is so important, because if you don't know it, you'll just be like, I'll just call sort again, whatever. Hey, look, it works. But your code is 20 times slower than it needs to be. 20 times slower is this thing was giving us 25% speed up, right? Something like that. Whereas, these things, if you go from n squared to n, if you're pushing front a lot, you want to use a dec, not a vector, right? It'll take you from order n squared to order n if you're doing n inserts at the beginning. So for 1,000,000 things, it's 1,000,000 times slower, right? It's like 1,000,000 times, that's way more than the optimizer, right? The optimizer is ballpark, and sometimes it'll eliminate a loop entirely. And the optimizer can do better than 25% speed up, but that's a reasonable ballpark for what you're expecting. For this, it's 1,000,000 times faster. And for this one, if you just switch out regular sort for bubble sort, if you implement BS, then you're 20 times faster. 20 times faster, not 25% faster, 20 times faster, because you know a little bit about the numbers and algorithms. It's a night and day difference. Like I said, I was hired by the WE department, the engineering department, and I took one of their highly unoptimal algorithms and optimized the hell out of it and made it just incredibly, thousands of times faster. And it's not like the W's didn't know how to program, because they do. They take 40 and 41, or the equivalent, whatever numbers those are at UCSC. But, they haven't had the algorithms class. They haven't had the data structures classes, And, maybe a little bit, maybe basic data structures, but they don't take junior level data structures. And so, people in the physics department would hire us, people in the WE department would hire us, and they already have programs. I worked for the bioengineering department. They have a program there they've been working on since the 70s, and they hired computer science people to come in and clean it up and make it faster and things like that, because these things make such a massive difference in running time. Okay. The double E's. What's funny about double E's? They're electrical engineers. So, yeah, let's just call this how to make code go fast. How about that? And way at the bottom of the list somewhere, you might have like assembly, And when you take CSI 45, you're going to learn how to like rewrite code in assembly. And that, could speed you up, a little bit as well. Usually the optimizer is good enough. You can usually just use the optimizer to make your assembly good. But there are times where you can still hand tweak assembly and get some extra speed. That's kind of bottom of the list. There's other things you learn in 45 to make your code go fast too. But the next two, the most important two, are caching and hashing. With a hyphen. Okay. Caching and hashing. So most programs be caching, just the way you call them that, W's. Yeah. I mean, that's what they're called, right? At Berkeley, they're EECS, EECS. They do electrical engineering and computer science, but one of my students, Nero, just got into Berkeley, so clap emoji from. So caching and hashing, yeah. So hash tables, now, right? You're going to do your competency exam on hash tables on Wednesday. Hash tables, it's a great way. You throw RAM at the problem and make the problem go away, right? Like you can trade off RAM for speed by using hash tables. If you need fast insert, search, and deletes, hash tables are just he got in. He's waiting to hear on San Diego and LA because I think you'd have to ask him, but if I was in his shoes, I would probably want to go to I don't know. It's hard to say. I really liked my time at UCSD. That was a great school, great professors, much better weather, much better weather. But Berkeley's Berkeley. It's the one of 6 number 1 computer science schools in the nation. So, yeah, get that Berkeley name on your diploma. UCSC is only 3rd in the country for computer science. So, caching and hashing. So hashing. So caching, though, is our topic really for today. How to make code go fast. Supposed to get SDSU after high school, but parents, yeah, state. I took a Air Force RTC class at San Diego State and had a lot of marching around and saluting people. That's my experience at San Diego State. Probably atypical. Probably most San Diego State students don't salute people. Walk around in outfits. You did a lot of hashing in high school. This is being recorded. The feds might, see this. I won't say your name in case the DEA wants to come after you for hashing. Okay, so caching. Okay, so let's talk about caching. How many people here have heard of Akamai? These guys. Technically, our server is on Akamai now. The Linode people got bought out by them. You put a lot of hashtags in your posts, right? Yeah, that's not the kind of hashing we're talking about. C hashtag, C#. So, Akamai is one of the most important companies in the world as far as the internet goes. And most people haven't heard of them. So what they do is they have like let's see if we can get a picture of it. Wow, look at this. Is this made by them? I hope not. The amount of money they have, they could afford better graphic designers. Man, that is, wow. Graphic design is their passion. Look at this. That is some word art right there. Okay, anyhow. So what? so the way Akamai works is they have Akamai servers all over the world. And so if you request a copy of like, I don't know, like CNN's website or something, right? Like you're like, oh, Don Lemon got fired. I wanna read all about it. Then what you do is you point your web browser at CNN. But what happens is Akamai is going to intercept that request. So if we trace route, www.cnn.com. I actually don't know if they use Akamai. I should check this first. So what will happen though is that instead of hitting up CNN's web server, what happens is Akamai will intercept that, and then Akamai will request a copy of CNN's website, and then keep a copy. They keep a cache, like you've heard of clearing your cache on your browser. Same concept. So what you do is you write it down. Because think about this: if you go onto Google and you search for news, what do you think the odds are that somebody else has searched for news in the last millisecond? Pretty good, right? And so the news doesn't change that fast. The news is, the news is the news, and new things are happening all the time, but it doesn't change every millisecond, right? So if I ask for the news, and Eric asks for the news, and Hockman asks for the news on Google, you can actually just not rerun your Google algorithm to find out the latest news. What you can do is, like, let's say I ask for the news, you can just write it down. You can write down the answer that's given, and then the next time somebody asks for the news, you just give them the copy of it. You guys understand? So rather than, like, if somebody asks you, hey, what is the shortest path from like here to, New York, right? And you like get some sort of like, let's navigate to the Clovis Roundup Community Newspaper, 111 Main Street in Los Angeles. Why not? The Clovis Roundup Community Newspaper, right? Google could just write down the answer here. So the next time somebody tries to route from 111 Main Street to the Clovis Roundup Community Newspaper, it could just give you the answer, right? And in fact, all of the shortest paths are probably pre-calculated, at least out to a certain level of detail. You do what's called an offline computation and actually write down the shortest routes between, a lot, basically anywhere to anywhere. And you can actually just write all that down. That's a form of caching, okay? Caching is when you do a computation Does that make sense? You guys all understand this? So like I could, if you asked me to like add up a million numbers, I could do it, whatever. But then I could just write it down. So if somebody asked me to add up the same million numbers again, I could just be like, here you go, here's the answer. And somebody asked me to do it, here's the answer. Because there is something called the 90-10 rule, which is that 90% of all the work you do is the same 10%. So out of all the searches Google gets, this is a rough rule of thumb, but out of all the Google searches Google gets, 90% of the searches they get are the same 10% of searches. Searching for weather, searching for news, searching for, I don't know, Bing. Wait, no, sorry, it's the other way around. When you go to Bing, I'm going to Google. No, I'm using DuckDuckGo to find Bing. Okay, here's the new Bing. All right. I need Microsoft Edge. No. And I'm going to use Bing to search for Google. So Bing Chat is now Bing, the search engine that does more than just search. Microsoft's tired of being the search engine to look for Google. That is amazing. That is absolutely hilarious. So if you search for Google on Bing now, before, it was like Google used to be the number one hit result on Bing, right? So now it still is, but now they're like, that is amazing. Bing shows off AI features that make Google Bard look basic. That is absolutely incredible. It's unbelievable. Okay, so then we use Bing to get to Google, right? And then if we use Google to search for the weather, it's going to use probably a cached version of it, rather than them running, whatever queries they use from the weather service to get the weather. The weather doesn't change that fast, right? So if I search for the weather, then Google is going to write down, if I'm the first person who has asked for the weather in Fresno, then Google will query the National Weather Service or wherever they get their weather data from, and then they're going to write it down. And then the next time somebody in Fresno asks for the weather, within, I don't know, a minute, like you probably want to refresh it every so often, right? At least every hour, but probably every minute or so. But if somebody else asks a millisecond later, they're going to get the same result. And if somebody asks a millisecond later, they're going to get the same result. And so I don't have to constantly be hammering the National Weather Service for data. I don't have to be constantly redoing computations. I'm just like, here you go. What's the weather? Here you go. What's the weather? Here you go. And that's why your browser has a cache in here that you can clear. What that is every time you download a picture, it caches it. And so the next time you go to download a picture, the same picture, it just loads it off disk. And that's why it's faster to visit a website the second time than the first time. The first time you visit a website, it has to actually download everything, probably from Akamai. Because, again, they have a cache, right? So if you ask CNN, it gives you the data and then it stores it in its cache here in Fresno. There's probably an Akamai node here in Fresno. Can't trace right out of here. Amazing. Never change. Okay. So, but yeah, probably the route goes to a local Akamai node and then it will return the data immediately. And so Akamai has nodes all over the world. Let's see if we can see where they have. Yeah, okay. So these are pictures of like where Akamai has their local nodes. And so rather than going across the country to CNN, which takes like a quarter of a second, like the speed of light is not that fast. It's really not. Speed of light's slow, especially when you're talking about going across the Pacific Ocean. If any of you guys have played Call of Duty online or played on like a different server other than US West, if you try playing in like the Asia Pacific servers over there, there's a lot of latency. There's a lot of lag. And so like rather than waiting for like a quarter second to like hit CNN server and it to come back, it'll hit the local Akamai edge and then return the result immediately. And Akamai distributes a copy of the CNN website. I assume that they're clients. I don't know if they are not. It has a copy of the CNN website on every cache in the world. And so everybody can instantly load the highest demand websites instantaneously. And then CNN itself, doesn't need to have a very beefy web server. Because all they really need to do is just be feeding the updates to Akamai, and then Akamai will distribute it through the world. And everybody can just hit the local copy of the cache. And sure, like maybe when CNN updates, you don't get the latest news a millisecond later. If 9/11 happens again, you might have to wait a second or two to find out about 9/12. But like we don't care because like the news isn't actually that fast. Like it's not like you need millisecond level speed on your news most of the time, unless you're doing like stock trading and things like that. And it's just like the weather; it doesn't change every millisecond. So what you can do is you can just write it down and reuse the results. Taking advantage against Singaporeans. It's a simulator, I think, made to look like Windows 7. Yeah. Am I in Windows 7? I'm not. No, this is Windows 11, dude. What are you talking about? Here's my start menu. What? So, I really hate the Windows 11 start menu. Like them throwing ads on and things like that is just unconscionable to me. So, yeah. I'm still using the same start menu that I have set up, like in Windows 95, really. So I have all my shortcuts and things like that all set up, so I can access most of the computer by hitting like 1, 2, 3 keys, and then it fires up my to-do list, right? So, yeah. So that's caching. Caching is one of the most important things. Yeah, and you can get more detail on how this works, but they have caches kind of all over the world. And if you're a major website, like most of them are going to be with Akamai or some equivalent. I think Google has their own CDN, content delivery network, and things like that. Is it a skin? It's a skin. Yeah, I could change it if it bothers you. I could change it. I heard about 9/11 first on the radio that morning when they didn't even know it happened yet. Yeah, I woke up Because in fact, I still have the same alarm I had during 9/11 right here. And I had the radio alarm turned on. And I'm like, why is there no music? Why are people talking? Yeah. He's so thrown off by it. Yeah. That's too funny. Now, I'll just go with any start menu that doesn't have all the advertising. Like, this is just so much nicer than their stupid thing. Okay. So, caching. Dynamic programming is a form of caching. Okay. So, let's do this. Move main.cc to old main.cc. Main.cc. Yep. Almost. Main.cc. There we go. Okay. So, we've talked about recursion before. And Fibonacci is one of those classic examples that you can do recursively. But what they don't tell you is the running time of that Fibonacci implementation is not good. So let's go ahead and implement it here. We'll do a fib index. And we will return. Okay, so if you guys all know the Fibonacci sequence, right? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, etc., etc. Each element in the Fibonacci sequence is equal to the sum of the two previous ones, right? So this is index 0, index 1, index 2, index 3, index 4, index 5, so on and so forth. So we're going to pass in the index, and we're going to return the Fibonacci number at that index. So, and we're going to do this recursively. So we're going to say if the index is less than or equal to 1, then we will return 1. Else we will return the Fibonacci of index minus 1 plus the Fibonacci of index minus 2. And so if we see out the Fibonacci of 10, we should get 89, I think. Doing the math right. There we go. All right. So 0, 0, 10. Yeah, okay. Good. Index 10 is 89. All right. Cool. So the trouble with this program is the running time. Every time you call fib, it calls itself twice. So every number higher you go, you do double the work. This is not order. This is not order anything good. This is not order n squared. This is not order n cubed. This is way, way worse. Every additional number you want to Fibonacci, you do double the work. So Fibonacci of 10, you do roughly 1,000 steps. For Fibonacci 20, you do 1,000,000 steps. For Fibonacci 30, you do 1,000,000,000 steps. You do Fibonacci 40, you do 1,000,000,000,000 steps. When it should be like 40, right? Like computing the Fibonacci of 40 should be roughly 40 additions, right? Like it should not be a trillion. It should be 40. This is order 2 to the n. Yes, thank you, Betancourt. It is order 2 to the n. This is garbage tier performance, okay? You never want to have an algorithm that is non-polynomial. You never want to have an exponential algorithm. Order n squared is okay, to a certain extent. Order 2 to the n is garbage tier. It is absolutely garbage performance. So let's just try out putting a few different numbers. The 20, the 30, the 40. $50, $60, $70. Did you guys see that? You want to see that again? YY9P. Maybe one too many. You guys want to watch this? Control V to do a vertical select of the columns. G to initiate a sequence. Control A to increment them. And need to do one more. Okay. I'm sorry, what? Vim Magic. Vim Magic. Control V to visual mode. Select a column. G to enter sequence mode. Control A to do incrementing numbers. Magic. Okay, G++, main.cc, run it, and you can see the running time gets slower and slower and slower and slower every time it outputs a new number. So we got to 40. Let's see if I have the patience to wait for 50. It should just have computed it instantly, right? So, yeah, I'm going to call it. All right. So what we can do, though, is cache the results. Okay? Because what's happening here is every time we do a Fibonacci, let's say we do the Fibonacci of 10. Fibonacci of 10 is the combination of Fibonacci 9 and Fibonacci 8. And Fibonacci 9 is the combination of Fibonacci 8 and Fibonacci 7. And Fibonacci 8 is a combination of Fibonacci 7 and Fibonacci 6. And what happens if I can draw this out, like the call chain on it, it looks like this. So the Fibonacci of 10 is equal to the Fibonacci of 9 plus the Fibonacci of 8. The Fibonacci of 9 is the Fibonacci of 8 plus the Fibonacci of 7. The Fibonacci of 8 is the Fibonacci of 7 and the Fibonacci of 6. And the Fibonacci of 8, wait, didn't I just say Fibonacci of 8? It's Fibonacci of 7 and the Fibonacci of 6. The Fibonacci of 7 is the Fibonacci of 6, Fibonacci of 5, and the Fibonacci of 7, wait, didn't I just say that? Fibonacci of 6, the Fibonacci of 5, Fibonacci of 6 is the Fibonacci of 5, Fibonacci of 4. Do you guys see how many times it's going to be repeating, like, compute Fibonacci of 6, compute Fibonacci of 6, compute Fibonacci of 6, compute Fibonacci of 6. You guys see that? It's repeating the same computation over and over again. Yeah, you have a sub-problem that is repeated. Anytime you have a sub-problem that repeats itself, that's when you use dynamic programming. So dynamic programming is a very simple concept that is hard to implement in practice, but it's a simple concept. So dynamic, if I could write dynamic programming is save your results for subcomputations. So this is a subcomp, right? You're trying to solve Fibonacci of 10. But to solve Fibonacci of 10, you're going to end up recomputing the Fibonacci of 6 over and over and over again. And so just write it down, man. And if you've already written it down, just return the value. You guys understand? It's like rather than recomputing Fibonacci of 6 over and over and over again, you know, we're going to do it again down here too. Like that is going to be Fibonacci of 6 too. Rather than doing it over and over again, just write it down, you know, and use a little bit of RAM, right? Save your results. This is a form of caching, okay? So this is a form of caching. Rather than repeating your results over and over again, you just write it down. And if you want to see what that looks like, it'll look like this. So, and this is what you're going to do for your next homework assignment, by the way. You're going to do something very similar to Fibonacci. It is called Pascal's triangle. So what we're going to do, we'll do this the proper way, I guess. We're going to make a vector, integers, and we turn 64 is 64 key. Named vec, of course, and in fact, we'll even initialize it to 1, 1. Start off the vector with the starting 2 elements of the Fibonacci sequence. And what we're going to do, this vector here is going to be the cache. This is like cache of results. So what we're going to do is every time we do a computation, we're going to write the result down. And then if we have a result, we don't need to redo it. We'll just use the cache result. So it'll look something like this. Vector of 64s named vector called by reference. And this is called by reference. It is not called by const reference because we are going to be modifying it. We're modifying the cache. We pass the cache in as a second parameter. If you don't want to use it as a second parameter, you can always make it a global. That's kind of garbage to your coding though. So, okay, so what we're going to do is we're going to first check to see if it is in the cache. If it is, return the value in the cache. If not, what do we do? So have we computed the Fibonacci of 6 before? If we have, we just cool. Here's the result. It is 1, 2, 3, 13. The answer is 13. If it's not, what do? Yeah, we got to compute it first and then add it to the cache after we compute it. Compute the value and add to the cache. Okay, so let's do this. All right, so if the index is less than vector.size, this is signed unsigned comparison. Let's make this size 2 then. If the index is less than vector.size, that means we have it in the cache. Because the vector index 0 of the vector is 1, index 1 is 1, index 2 is 2, index 3 is 3, index 4 is 5. So the index is and the size go with each other. Okay. So if the index is less than the size, we have it. So we're just going to return vector.at_index like that. And then if it's not, we can just do this. We compute the sum, and we have to pass the vector in, of course, to it. Back here, and vector here. So we're passing the cache in with it. So we're going to compute the sum, and then we're just going to add it to the vector. So vector.pushy backy, add it to the cache, and then return the sum. And that's it. It's about the same number of lines of code as before, right? I mean, I have a lot more comments here, so you can understand it. But conceptually, does this make sense to you guys? Like, I'm just checking to see, hey, is it in the cache? If it is, we just return the value. And if it's not, then we do the computation. We add the fib of 5 and the fib of 4. However we get those values, we get those values. And then we add that to our cache. And we return it. So let's see if it works. Right, we need to do this. YY9P. Let's do some Vim magic again, if you guys are ready for this. Control V, G, Control A, and there we go. Compile and run, and there you go. It went from being an order 2 to the n algorithm, which is like heat death of the universe to compute that last number there, to order n, which means it was able to compute it in roughly 100 operations. Okay. This is called memoization. Yeah, memoization is just another word for caching now. So memoization means writing down on a piece of memo paper. It's caching. Okay, so memoization turns this into an order n algorithm. This is pretty big. Like, going from like a exponential algorithm to an order n algorithm, it's like pretty, like, that's an amazing, like, we went from heat death of the universe to like instantaneous. Like, there is nothing, no optimizer, like, you know what I mean? Like, yeah, oh, my optimizer makes the heat death of the universe run 25% faster. Oh, okay. Yeah. if you change, if you have that horrible algorithm, and you make it heat death of the universe minus 25%, it's still going to run forever. But if you pick the right algorithm for the job, if you do caching, and you drop that order 2 to the n to order n, it is all the difference in the world. Like, there is nothing faster than that. And that's why understanding data structures is so important. That's why understanding caching is so important. All of these things are like topics in computer science. Like, you might be wondering why computer science is a 4-year degree, right? Because after this class, like, you're not going to take any more like learn to program classes. Like, you know C++ now, at least the language side of things. You know how to do a for loop. You know how to do a function call. You know how to do lambdas, right? You guys all love lambdas in this class, man. And then, like, you might learn other languages at a certain point, but this is it. Like, you've got a couple weeks left, but basically, inherit, like, you probably don't know it well, but like, this is the end of your learn to program experience. After this, computer science turns into this kind of stuff. Like, how can I make my program not run for 1 billion years and take place in less than a millisecond instead? That seems kind of useful. So, the rest is figuring out how to not break things and how to fix them. Well, it's like algorithms. Like, how do there's a lot of like really bad solutions to things that are like brute force. Like, try every chessboard position, right? Like, great. There's a trillion chessboard positions. You need something better than that. You need something intelligent. If you're going to be writing a chess computer, you need to really like think about it and think, how can I have it search, the board space, faster than other people. Ken Thompson, who's one of the inventors of Unix, he got into like chess machines like back in the day, if I'm remembering this right. And so he had access to some of the fastest computers in the world, and so he would win at a lot of the computer chess tournaments because he had access to more computational resources working at Bell Labs than other people did. 5 times winner of the ACM computer chess tournament. Yeah. 78, 80, 81, 82, 86. Yeah. So, yeah. So yeah, Ken Thompson's a legend in the field, and he and Dennis Ritchie made Unix, and like you can find his videos online of like how he went about doing it. It's just inspirational. He threw more RAM at his problems. He threw money at the problem. That's what it amounted to. Because he had Bell Labs on his side, so everybody else was like building these things with soldering irons in their garages, and he had like military grade hardware to play around with. So Thompson was interested in chess, but he didn't like losing, and he also didn't like winning, because he felt like, since he was kind of an amateur at it, like he was kind of like making people who took it a lot more seriously than him like feel bad. That's why he got into computer chess, so he could actually became a technical problem. So DS and algorithms to pass interviews, yes, yeah. If you want a job, like this kind of stuff is huge. Yeah. Okay. So do you guys kind of get what we mean by dynamic programming? We have this vector here, and every time we compute like the Fibonacci of 10, we just record it. We just write it down, and then we can just check to see if it's in the cache. If it is, we return the value. That conceptually, does that make sense to you guys? You got a whole Zybooks on this topic due on Wednesday, so if you don't get it now, get it by noon on Wednesday. It's a simple concept. Like I said, it's a simple concept. Basically, just write down your results. Like, if you've, especially if you keep repeating the same computation over and over again, write it down and then reuse it. Because 90% of your work is going to be reused. Or 10% of your work is reused, 90%. But in practice, it's actually kind of complicated, right? Like my professor who taught me dynamic programming, TC Hu at UCSD, who did ballroom dancing, by the way. I'm not the only computer science professor into ballroom dancing. TC Hu is a good dancer too. By the way, Camilla is starting a ballroom dance club on campus, and so she needs 5 students to put their names down to be one of the inaugural members of the ballroom dance club. And so send her a message on Discord if you wish to join the inaugural class of the Ballroom Dance Club at Clovis Community College. Wadden is also cool. Yeah. Very cool. Anyhow, so TC Hu was my dynamic programming professor, and he told us at the start of the quarter that I had him for dynamic programming. He's like, I just got a new textbook on dynamic programming, and since I have written textbooks on dynamic programming before, I'm professor who specializes in the subject. I'm like, all right, I'll just go through and run through the homework problems and just see how I do. And so he gets number 1. It's like, oh, that's easy. Boom, knocks it out. 2, no problem, knocks it out. Gets to question 3 in chapter 1 and goes, huh, I don't know how to solve this. And dude was brilliant, he was a smart guy, so like a lot of students get like imposter syndrome because they're like, oh man, I'm flummoxed, by this thing. But TC, who was a guy who specialized in this very topic, he worked for Intel, using dynamic programming to make their chips layout more efficient and things like that. Like this was his, like he wrote textbooks on this, like in papers, and he got to question 3 in chapter 1 of a new dynamic programming textbook, and he was like, all right, I'm gonna look this up in the back. So never beat yourself up too much. We all go through it. One of my students last semester was like, you don't know what it's like to struggle. It's like, I'm a computer science major, man. I know all about the pain, of not getting something immediately. So, yeah, so dynamic programming it can be hard in practice, like finding where the similar computations are, but I know the life of pain. Yeah, the wheel of pain makes you stronger. Like when you struggle and succeed, it definitely builds character, it builds strength. Okay, so let's talk about your next homework assignment. So your next homework assignment is going to be doing Pascal's triangle. Pascal's triangle, for those of you that don't know, it's very similar to the Fibber sequence, the Fibonacci. The Pascal's triangle is it's going to be a 2D array, and each element in the array is equal to the sum of the people diagonally above it. So northwest and northeast. You can imagine this on a grid with like a space in between each one to make things easy. And so you can see like this guy here, 70 is the sum of 35 and 35. 15 is the sum of 5 and 10. So it's kind of like a 2D version of the Fibonacci sequence. And you might notice the weird coloring here. And this is actually what you're going to be graded on. You guys are actually going to do an art project using Pascal's triangle. And I think what they've colored here are all numbers divisible by 3. If I'm looking at this right. I have no idea. But it looks like the numbers divisible by 3 are in white. Everything else is in gray. And you might notice that it's forming the Triforce. So, also known as the Sierpinski triangle. And what you're going to do is you are going to do Pascal's triangle, and you are going to output it. You're going to modulus it, right, by one form or another. And it looks like even numbers are colored yellow here, and odd numbers are colored blue in this one. That's even cooler. That's neat. Let's see. That's cool. I don't know what that's all about. 114. So there are lots and lots of ways that you can actually do this, and so it's an art project. So you guys are going to have to do. You're going to have to write the code for Pascal's triangle, and you're going to have to use bridges to visualize it. So let's see, 128 rows. So this one they did divisibility by 8. Okay, so you can modulus the values however you want. Modulus by 10, modulus by 2, modulus by 3. You're going to do a couple different ones. And I want you to do creative mode or endless mode, depending on how well your coding goes. It might be endless mode. Yeah, there's an input tester. Your input tester is going to be like, can you do this right? And so here they've got like a bunch of different colors on it. I've got some starter code that'll help you guys, but it's an art project. This is actually an art project that I did when I was in middle school. I went to these like summer school enrichment things, and they had us do Pascal's triangle, and they had us like write down, color it, and we had to come up with a color scheme. If it's divisible by 5, colored in with this. If it's divisible by 3, colored in with this. And we did it on a snowflake, so it was actually symmetrical in 6 directions, and it created these really beautiful artwork, fractal snowflake kind of things, and yeah, like you get these like Triforce looking shapes out of them and stuff like that. It's really neat. And so partially reminds you of Zelda, and partially reminds you of a grandmother like crocheting things. Yeah, the Triforce symbol is the symbol of the Hojo clan, which is the people that kind of like took over from Yoritomo and all those guys after they were like the first shogunate. So sort of like a military coup against the emperor kind of, and the Hojo were like the successors to the Yoritomo's people, and their symbol was the Triforce character. It was weird because like I was in Kamakura money washing, so there's actually a place there where you can do money laundering, like quite literally money laundering. Like you actually wash your money, and like I'm not joking. It's literally money laundering, and everywhere you go there's like these like, you know, the symbol of the Hojo family, and I was just sort of like, is this Zelda? Like, what's going on here? Yeah, and then I got to learn that the Zelda Triforce was actually the symbol of the Hojo clan, and I got to learn all about the history of Kamakura and things like that. It's a pretty cool place to visit. I don't remember the name of it. What was it? Fukushima? Is that it? Okay. I don't know. I don't remember the name, but really beautiful place. Kamakura is amazing if you ever go to Japan. All right. So, yeah, I'm going back to Japan next summer. This summer is Hawaii. All right, so let's talk about APIs a little bit in the last couple minutes. So you guys have all probably heard the term API before, application programming interface. So what an API really is, it's just a list of functions that are available. It's like, you know, when we talked about proper class design, you have like an interface and then an implementation. So you have a header file, you have an implementation file. So the header file you could consider like an API. Like, here are the functions that exist. You don't need to worry about how I'm doing them. You just need to know that they exist and what they do. So here's a function that'll play a sound. Here's a function that'll, you know, make an explosion appear on the screen. You have no idea how I am actually implementing playing a sound. You have no idea how I'm implementing drawing the explosion. All you need to know is that if you give me a WAV file on disk, I will play that sound for you. That's an API, okay? An API is just a collection of functions. And if you've heard about API in the news recently, it's because like Twitter has been charging people to use their API. Twitter's $42,000 per month API outprices nearly everyone. Tiers will start at $500,000 a year for access to 1/3% of your company's tweets. Researchers say that's too much for too little data. So, one of my friends in the Bay Area, fairly left-wing guy, he created a Twitter bot using their API. He worked for a different Jack Dorsey company called Square. Makes like those cash registers and things like that. And so what he did was he wrote a bot that would use the API, the application programming interface, to grab tweets from like 100 top conservative people, and then he would like wrote something that kind of like munged them together, and then it would tweet out like, you know, man, I can't believe what Congress is up to these days. We need to go back to our family values and things like that. It kind of reminds me of like the robot DJ from The Simpsons, who kind of anticipated ChatGPT, or the DJ 3000. Yeah, it could happen. It has happened. It's called ChatGPT. But like DJ 3000. Inane chatter. So like they hit that button, it's like, hey, how about that weather out there? Or they would hit it and it's like, those clowns in Congress are doing clown things again. And they're like, how does it keep up to date? You know, so he used the API to, like, you know, basically create a chatbot. Not really a chatbot, but like a, you know, sort of a conservative Twitter bot. And he ended up getting like 100,000 followers. I don't know exactly how many he got. But you know, Reddit is now charging for its API access. So companies that crawl Reddit for data and don't return any value will have to pay up. They have a price on here. They're going to do AI themselves. That's probably why they're going to be. They don't want to compete with other people. Monthly $1, then $30 a month. Okay, all right. The CEO blames AI. Yeah, because like all these AI companies have been using these data sources. They've been using Twitter and Reddit as sources of data. In fact, Bridges has a Reddit API now where you can like get information from Reddit using Bridges. It's kind of cool. And spoilers for Portal 2, Wheatley Laboratories. Hopefully still free for small devs. I don't think Twitter is. Yeah. And so I don't have to go to the website. I want just to scrape images. Yeah. So that's what an API is. And so another thing you're going to learn on this lesson is just how to read the documentation on an API. So Bridges has a documentation page. In fact, the getting started page is pretty good. And you can get instructions on getting set up, which you don't need, like the C++ API. I will post this here on Discord. And basically, it tells you everything you need to know. And so one of the skills you need to develop as a computer science person is the ability to go through documentation and be like, okay, where's the thing I'm looking for? You know, this is the life of a lot of computer science people. Like, okay, where's the thing? Where's the thing? I'm trying to find the thing. Amenity, that doesn't sound like a thing. Where's the thing? There's a grid. Is it a grid? Is that what I'm looking for? No, that's not the thing. No. Color grid, that's the thing. Okay. And so you can use a color grid on Bridges to visualize the Pascal's triangle. So let me give you an example of what that would look like. Pascal's triangle on Bridges using a color grid looks like, where is it? Here it is. Looks like this. Okay. And you are going to use whatever color scheme you want. You're going to be graded on your artistic ability. Obviously, you have to get the coding done. You also have to do it using dynamic programming. You have to do it recursively, and you also have to use dynamic programming so that it doesn't take until the heat death of the universe to do. So what you're going to do is, if somebody asks for this cell value, if it has not been computed before, you compute it. If it has been computed before, you return the value. And so it's the same notion as Fibonacci. I'll post the copy main.cc up in the public dynamic dp fib. See? And so you can take a look at how the dynamic programming Fibonacci goes right here. And the assignment's very similar, but you're going to want to look at the Bridges API and see like how that works. What you're going to do is you're essentially going to create a color grid with a certain height and a certain width, and that's going to create that backdrop here. It's a certain number of squares wide, a certain number of squares high. And then you use the set function on it somewhere. Get width, get height equals color grid. Each element of it is a color. IP found grid set. And so you can use the set function to set at this row, at this column, this color. And if you want an example, and another thing that computer science people use all the time is we look at demo code. Okay, so I pushed out some demo code for you guys. Don't ask me when is Bridges Mountains due. It's not. This is a CSI 40 assignment, but I'm pushing it out so that you all have a copy of it. And you can see that the code in here has a color grid in it. It is going to new a color grid. You don't necessarily have to new it, but you can new it if you want to. It news a color grid with a certain width, a certain height, and it will set at this row, at this column, this color. Okay. Colors range from 0 to 255 in each of the 3 channels, red, green, blue. And so 000 is black, 255, 255, 255 is white. This one is setting red to full, blue to full, and green to 0. And so red plus blue is purple. And so it's going to draw a purple box at this row, at this column. And for this one, it's just going to give some sort of monochrome thing like 10, 10, 10, 20, 20, 20, whatever. So this is indeed purple. Okay. So this demo code here will kind of, like, that's typically how I begin programming. Like, I didn't know bridges before I started doing bridges either. Nobody taught me. I didn't go to any workshops. So you're going to get the computer science experience, right? You look at the API documentation, you look at the demo code, and you're going to put together completely greenfield from scratch code that will upload a Pascal's triangle or 2. You're going to do 2 of them to the Bridges website. You're going to link to me your 2 triangles and your source code showing me that you used dynamic programming and recursion. And if you do that, you get 10 out of 10. If your triangles are particularly beautiful, you get more. You'll get extra credit. Web development's almost entirely demo code. Yeah, it is. And but there's documentation. Documentation is sometimes really good and it's usually pretty bad. So it is usually you find somebody who's done something similar to what you've done. For this case, Bridges Mountains is very similar to what you've done, and you modify it from there. Okay. You guys all understand? I want you to come up with something pretty. Do some sort of math art. Okay. And it's your job to read the documentation, read the sample code, code something up from scratch. Your code's not going to compile right because you didn't look at the make file, so look at the make file to how to get the code to compile correctly. Math art is your dream degree. It's a thing. Computer graphics is really math heavy, and computational geometry is like math and computer science and gaming and 3D art kind of all mixed together. It's kind of a cool world to hang out in. Computer graphics is fractals. Yeah. Fractals are computer graphics. Yeah. So there's a lot of fun, beautiful things you can do with fractal art, things like that. Sierpinski triangle, like what we're doing right now, is fractals. Yeah. A lot of computer graphics classes use fractals assignments. Yeah, like this one. Technically, we're just doing addition, but it turns into a Sierpinski triangle, which is a fractal. Do you have to use bridges? Yes, that's part of the assignment. Is learning how to read an API documentation. That's just one of those clutch skills that every computer science person needs to have. And it's something I've been hammering a lot with my 45 students this semester. Make this ultrasound work. Here's the website that has all the source code and demos on it. Go. Rather than me sort of doing it all for them, it's your last semester with me, so I'm trying to get the birds to leave the nest and to fly on their own and things like that. Because in the real world, I had to do all this stuff from scratch, right? Nobody's holding my hand. When you're an actual computer science person out in the world, you have to learn how to read documentation, look at source code, and make it work. So this will be a little not too hard assignment, I don't think. So, you wondering if you could alter your triangle rasterization program? That'd be interesting. Yeah. Well, you can alter your triangle rasterization program to use bridges. Yeah, that thing. I think that'd be fun. If you wanna do that instead of the Pascal's triangle, yeah, I'll accept that. It's kind of cool computer art. Yeah, you can do that too, Aaron, if you want. But yeah. Okay, so that is it for today, guys, and I will see you guys on Wednesday when we will do a hash table competency exam. All right, peace out.